All right, so let's look at this question. It's saying arrange the following elements in the increasing order of their metallic character. And we have been provided with silicon, beryllium, magnesium, sodium, phosphorus. Oh, so that's a weird bunch. It's not a single period or elements of a single period or elements of a single group. It's kind of a very randomized hodgepodge bunch we have got here, right? But even within this bunch, we can further, segment them into two buckets. We can say that, what, this bunch here, this bunch is obviously going to be more metallic as compared to these two, right? Obviously, correct. Okay. So yeah, this bunch is going to be, one of the last bunches. This is going to be the fort runners. These are going to be more and more, right, as compared to this and this, right? The bottom ones over there, these are less metallic, obviously, right? Okay. But within these two, if you ask me, right, if you ask me about the metallic character, right, I would say that, between silicon and phosphorus, phosphorus lies towards the more right of the periodic table, right? We have silicon, phosphorus, sulfur, chlorine, right? So we have silicon, then we have phosphorus. It lies towards more right. And for that reason, the metallic character in phosphorus is less as compared to silicon, right? Okay. Between these three, however, we can look at beryllium directly and cast it out right away because it belongs to the second period and it is also an alkaline earth metal, and it also has a very small charge. It has a relatively, when you compare it with magnesium and sodium, it has a relatively high ionization energy as well, right? So it's going to be lower than these two. It's going to be, lower than these two. But what about between these two, right? What about between sodium and magnesium? The same logic that we applied here, that sodium comes and then magnesium comes, right? So magnesium is right of sodium. And for that very reason, we'll say that, what, sodium has more than magnesium, right? Metallic character. Magnesium has more than beryllium. Beryllium has more than silicon, and silicon has more than phosphorus, right? So what we are looking for essentially is PSIBE. So let's start with that. This is not going to be there. PSIBE. Then we are looking for MgNa. Oh wow, MgNa. So yeah, option B matches. This does not match and this does not match. And with it, we have solved this question, and the option here, the correct one here, is B for Bangalore. All right. All right, let's take a look at this question, right? It's saying the compressibility factor for a gas under critical conditions is going to be equal to what? Although we remember this value and we know what the value is going to be, it's going to be 3/8. Let's still solve it out because Z is usually equal to what? Think about it, right? So Z is usually equals to what? PV molar real divided by RT, right? Okay. And in a critical scenario, we are going to have PC VC divided by RTC. Remember, this VC, this is a critical molar volume, right? This is still a molar volume, just that at critical conditions. Also, we know one more thing, right? That at critical conditions, right? The values in terms of A and B, at critical point, the values in terms of A and B for PC, VC, TC are something like this, right? VC here is equals to 3B and TC here is equals to 8A divided by 27RB. This is what we get, right? So yeah, this is what we have. Is it not? Right? Okay. So when we put in these values here, we have A by 27B square that gets multiplied by 3B here. And in the denominator, when we look at it, we have R here. Alongside what do we have? We have 8A divided by 27RB. All right, friends, let's start canceling stuff out. The favorite thing, I like to do. So yeah, A gets cancelled out, R gets cancelled out. What else do we have? 27 gets cancelled out. Okay, this B also gets cancelled out. And as a result, if you take a look carefully, what you're getting over here is at critical conditions, is coming out to be, this is cancelled, A is cancelled, 27 is cancelled, B square is cancelled. only 3 is left in the numerator. Divided by R is cancelled, A is cancelled, 8 is there, 27 is cancelled, R is cancelled, and B is also cancelled, right? So can you look at all of these over here? Do you realize what we are trying to do? Do you see, right? Okay, and this is, essentially what we have, right? Let me just get all of these elements back together. All right, I'm finding this fun actually, to not delete the actual values written over there and still be able to get rid of the Gibbs, right? Okay, so yeah, we get this, and the value is 3/8, and the correct response to this question is option A for Allahabad, right? Okay, this question is concluded. All right, let's take a look at this question, right? It's saying, what is the nature of chemical equilibrium? The options are static, dynamic, irreversible, both B and C. First of all, not irreversible, right? We need reversible. We need reactions that counter each other's effect out. Now, while I've said counter each other's effect out, remember we talked about rate of forward and rate of backward, and we say forward reaction consumes reactants and produces products. Or maybe calling them reactants and products is also wrong. So let me just give you some references. The forward reaction here consumes A and B and produces C and D. And the backward reaction here consumes C and D and produces A and B. Right? When these two rates are actually exactly same at that point of time, the forward reaction, the consumption of A and B by the forward reaction is balanced by the production of A and B by the backward reaction. So A and B concentrations do not change. Similarly, if we talk about the C and D, right, the consumption of C and D by the backward reaction is counter-affected by the production of C and D by the forward reaction. And in that manner, we actually do not observe any change in the concentration, right? From the outside, it looks like the concentration is not changing and the reaction is not there, and chemical activity is not showing any change from the outside. Outside it looked like. And so we call it chemical equilibrium. But we know that in reality, it is dynamic because two opposing reactions are there, and at equilibrium, they are indeed cancelling each other's effect out, right? With that, option A is not true because option A means, no reaction is happening. No, that is not true. In chemical equilibrium, reactions do happen, just that two opposite reactions happen which counter each other's effect out, right? Irreversible is also not true. And since B is only true, B and C are not true, so D option is also incorrect. And with that, we have option B for Bombay, as our correct response. All right, let's take a look at this question, right? It's saying a valid Lewis structure of this particular thing cannot be drawn without violating the octet rule. Okay, fine. Let's have a look. So, look, looking at the question directly, right? I get what the answer is. Why? Because look at phosphorus. It has 5 electrons, right? It forms, 3 bonds. It gets a complete octet. So this is sorted, right? So it cannot be drawn without violating, so it can be drawn. So this is not the answer. When we look at carbon, it has 4 valence electrons. It is forming 4 bonds with chlorines, and that part is also sorted, so it is not violating the octet rule. So yeah, this is can also be drawn without violating the rules. So the question is cannot be drawn. So yeah, this is also out of the race. Talking about ClF3, however, right, it has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. It's forming bonds with 3 of them. Now, if you take a look over here, just try and count, right? I'll just write, this is 1, this is my friend 2, this is 3, this is 4, this is 5, this is 6, this is 7. Now, this here is 8, this here is 9. Oh, this here is 10. Oh, what happened? Octet got expanded. This is a case of superoctet. We are violating the octet rule, and for that very reason, option A here cannot be drawn without violating the octet rule, right? And for that very reason, option A here is indeed the correct response for this particular question, right? Okay, and with that, this question is sorted. All right, let's take a look at this question, right? Okay. It's saying the standard reaction Gibbs free energy for a chemical reaction at an absolute temperature T is given as this equation, correct? Okay. Where A and B are non-zero constants, which are the following true? Okay. Exothermic, endothermic. Oh, okay, fine. So this is a very easy question. Take a look at this. We remember this equation, right? Remember this equation? We had this minus T delta S naught reaction, right? Okay. Now take a crazy look and try and compare, this equation here with this equation here. You'll realize that this entity is your A, right? Your A essentially is delta H naught reaction, right? And similarly, this entity over here is basically B, your delta S naught reaction, right? Okay. So exothermic, if A is more than zero, so this entity, this becomes wrong here only, right? Anyway, why is B being discussed when we are talking about exo or endothermic, right? Endothermic, if A is less than zero, no, then again incorrect. But why is B there? B shouldn't be there, right? For entropy, delta S reaction plus minus, that shouldn't matter with the reaction being endo or exothermic, right? Okay, endothermic, if A is more than zero, yes, indeed, because delta H needs to be positive, right? And exothermic is B is less than zero. No, entropy, no. Had it written A is less than zero, I would have ticked D. Also, the correct answer would have been C and D if it had A instead of B here, right? In that case. Right now, no. So D option is also incorrect, and the correct response for this question is turning out to be option C, C for Calcutta.